Chapter 6 is titled Rational Exponents. In this chapter, we'll take a look at exponents that are in fraction form, we'll look at different types of radicals, we'll evaluate expressions, and we'll graph functions. We'll also look at domain and range, and look at inverse of functions. So there's a lot happening in Chapter 6. Lesson 6.1 introduces us to nth roots and using rational exponents. We start off with this pretty big chart of different exponents. We have perfect squares, perfect cubes, and then we have fourth powers, fifth powers, all the way up to sixth powers. So we call this the powers chart or power chart. And what this does is just gives you an opportunity to look up an exponent for a base faster than even typing it into your calculator. For example, if you look at the problems down below, if we utilize 4 to the fifth power, what you need to do is just go to the power chart that matches the exponent, so that would be the fifth powers. If your base is 4 and you raise that to the fifth power, you just get 1024. Just using it to look up numbers faster, like I said, than typing it into your calculator. 3 to the sixth power, you can multiply 3 by itself 6 times if you want. But if you look at the sixth power column with a base of 3, that gives you 729. Even if you have negative exponents, we still apply our negative exponent property by taking the reciprocal of the base. Now, we worked with perfect cubes a lot back in Chapter 5, but looking at our perfect cube column, 9 cubed is 729. So notice 729, that's the same number that we had with that base of 3. There's a connection with those two different types of bases. But what makes this power chart even more unique is evaluating different roots. We know that the square root of 36 is a perfect square, it just equals 6. But 120 isn't a perfect square. Now, there are lots of ways that you can go about finding the perfect square factors of 120. And I'm fine with whatever method you feel you are best at. I like to break it down to find numbers that are perfect squares that go into 120. So I know I could do 1 times 120, 2 times 60, 3 times 40. I know 4 goes into 120 30 times, and 4 is a perfect square, but I want to see if there's anything bigger. Let's see, I know 5 would go in 24 times, 6 goes in 20 times, 7 doesn't go in, 8 goes in 15 times. There are so many factors of 120. 10 goes into 120 12 times. So when I look at all my factor choices, I notice that the only factor set that has that perfect square is 4. So if I use these two numbers and break down the square root of 120 as 4 times 30, 4 is that perfect square that can come out as a 2. The square root of 4 is 2. Now 30 on the inside doesn't break down any further. So the final simplified form is 2 square root 30. But when you get into higher ordered values, you have to look at that power chart a little differently. So let's try a couple that have different types of roots. 3 on the corner with the 8 means the cubed root of 8. So that means you're going to work that power chart backwards. The cubed root means you go in that the cubed column, but now you look where the answer is 8. What number to the third power equals 8? That would be 2. 2 to the third power equals 8. Therefore, the cubed root of 8 is a perfect cube answer. But they won't always be perfect cube answers, like the next one, the cubed root of 128. Now, if you look up on that list, 128 isn't a perfect cube, but there are numbers that go into 128 that are. So since there's a 3 in the corner, look at the cubed column. And then we want to try to find numbers in that column that go into 128 evenly. Well, 1 times 128 won't do us a whole lot of good because neither of those are perfect cubes. Well, the 1 is, but that really doesn't simplify. But watch this, everybody. If I go to 2, 2 times 64 goes into 128, their factors, and 64 is a perfect cube value. And that's going to be the biggest one we'll find because 2 can't be simplified any further. Therefore, that right out of the gate is our set of factors. Now watch how I write out this next step. If we want to do a cubed product of 64 times 2, I like writing the perfect cube first, but you can write them in either order, doesn't matter. We'll take out the cubed root of 64, but be careful, not as 8, but the cubed root of 64 is 4. So 4 goes on the outside. We write that root symbol, but that 3 has to go in the corner for the cubed root, and then 2 is left over on the inside. So it's the same kind of answer we got with the square root of 120, but we're looking at cubed roots instead of square roots. And if I go to the next one, we have fifth root of 32. So fifth root means we're going to go into that fifth powers column and see if 32 is on, oops, I forgot to spell powers. Don't worry about the R. There we go. The fifth root of 32 is a perfect fifth root. 2 to the fifth power equals 32. Therefore, the fifth root of 32 just goes right back to 2. We'll work with these enough so that some of the common answers that you'll see will happen really frequently, so you'll see them several times. Let's take a look at the definition of real nth roots of a. If you have nth root of a, you put the radical symbol, a goes on the inside, and n is in the corner. So n is known as the index of the radical. And it's however many times you need to multiply a number to equal that value on the inside. A, that original base, is called the radicand. Oops, I totally spelled. What's with my spelling? Here we go. It's the radicand. And then the root symbol itself is just the radical symbol. So I'll just say radical / root, since it's different than your exponents. Now, depending on the type of index you have, some values will be defined, but others won't be defined. It says let n be an integer, and it has to be greater than 1. Ooh, I don't like that either. All right, greater than 1. There we go. And let a be a real number, so we know that we're not dealing with imaginary solutions. If n is an even integer, so even values, and a is is less than 0, what happens is you have no real roots. Here's an example. We've done this before. When we did quadratic formula and got something like the square root of -17, that means no solution or no roots. We can't take the square root of a negative number. You could also try a different type of even root, like the fourth root of -21. You can't multiply a number 4 times and get a negative answer. So there are no roots for the fourth root of -21. Now, if you change your radicand value to 0, so if a equals 0, well, there's really only ever going to be one solution for that answer. The square root of 0 is just 0. There's only one location on the coordinate system or a number line that would have that value. And then we've also worked with the next one. If a is a number that's greater than 0, we will always have 2 real nth roots. For example, when we did quadratic formula, if we ended up with the square root of, let's say, 50, that always equaled, we had the plus or minus, remember, out in front of it, and then we could simplify that into 5 times the square root of 2. But if you also have something like the fourth root of, let's say, 81, that would be true for both positive and -3. You could take 3 to the fourth power and get 81, and you could also take -3 to the fourth power. And those are the rules you apply when you have even integers for your index. If your integer is odd for your index, like a cubed root or a fifth root, we can't have a 1 root, that doesn't change anything at all, but a cubed root or a fifth root, when a is odd, or n is odd, you're only going to have, notice, one solution each time. So if a is less than 0, you're going to have one real root, like the cubed root of, let's say, negative 8. That would equal negative 2. If you multiply negative 2 by itself 3 times, you'd get negative 8. And like the second one on the left column, if a is 0 and you take, let's say, the 5th root of 0, again, you're only going to get one answer, and it's just 0. So it's kind of a consistent solution. And now, unlike the left-hand side, if you have a number for a that's greater than 0, you're still only going to have one root answer. Watch this. If I say, what is the cubed root of positive 125? The only answer where that's true is positive 5. We wouldn't be able to take negative 5 to the third power and get a positive answer. This is just kind of a way to define how to calculate nth roots of different values. Sometimes they have perfect answers, but sometimes they can only be simplified. When asked to find an indicated root, you're going to want to check the power chart. So find the indicated real nth roots of a. If n equals 3 and a equals negative 216, what this means we're asked to do is find the cubed root of negative 216. So negative 216 is the radicand and 3 is the index. Now on the power chart, let's look at our perfect cube column. I see 216 when it's positive 6 to the third power, but we want our answer to be negative 216. When your index is odd, you have just one solution. So if the radicand is negative, so is our answer. It just means we're going to have negative 6 as a solution. That means if you took negative 6 times negative 6 times negative 6, you would get negative 216. For the next one, now we jump up to n equals 6, and we want our a value to be 64. What this means is we're trying to find the 6th root of positive 64. Now in that 6th powers column, do you see 64 as an output anywhere? I see it at 2. But because our index is even, we could have positive 2 or negative 2 raised to the 6th power, and we'd get positive 64 as our radicand. All right, next one. If we're looking at n equals 4 and a is negative 81, we're trying to find the 4th root of negative 81. Now it's true that in the 4th powers column, we see 81, but we can never have a negative number if our index is even. Therefore, this one is not possible. There are no real roots to any even index with a negative radicand. All right, I'd like you to try the 3 at the bottom. Set it up into the radical format. Use your power chart as a guide if you need to. When you're ready, press play. Did you get 0, 7, and 0? Remember, anytime your radicand is 0, the root, no matter if it's odd or even, will just be 0. In the middle, the cubed root of 343 equals positive 7. That's in your perfect cubes column. Now that last example, if you're taking the square root, that's the only time we wouldn't put the index number in the corner of the radical symbol. So when you just have a plain square root, that just means n equals 2. But we don't write it in unless it's a number greater than 2. Considering our radicand was 0, the answer was just automatically 0. Let's see now how this ties into rational exponents. Rational is just another way to say a fraction. So yes, we are in fact working at fraction exponents, or working with fraction exponents. It says let a to the 1 over n be the nth root of a, and m is a positive integer. If you have a to the 1 over n power, what that means is you're taking the nth root of a. The 1 just means you'd raise it to the first power, and that doesn't change the answer at all. So if you have a radical, you can also rewrite it in this rational exponent form. Now if the number in the numerator is different than 1, like the next example, a to the m over n, we can actually write this in one of two ways. We could write this as the nth root of a to the m power, but another way that's useful is when we're trying to simplify terms that have the m and the n as different numbers. Another way that's pretty useful to use this is take the nth root of a first and then raise your answer to the m power. It works in either order, but I'm going to kind of make that n a little bit clearer right here. So I'm going to fix that for you quick. The nth root of a to the m power. Both of them give you the same end result. Even if you have a negative exponent, we've worked with these before, when you take the reciprocal of the base, watch this. This deserves a really big star. When we take the reciprocal of the base is a. It has nothing to do with the m and the n. That means if we do 1 over a to the m over n, that's how you make that exponent positive. We don't flip the m and the n. But now it looks like that middle section. So this could be one of two choices. You could do 1 over the nth root of a to the m power. I know it's really tricky to write these all out. Or you could do 1 over the nth root of a, then to the m power. Either one of those would give you the same answer. Recognize, though, that your answer would be a fraction. All right, let's put this to the test. All we're going to do first is just kind of rewrite forms. It says write each expression in radical form. So let's take a look. I'm going to zoom this out to make these a little bit bigger to work with. There we go. 12 to the 1/3 power. That's like saying a to the 1 over n. If you have 12 to the 1/3 power, we're just going to write the radical symbol, and 12 is our radicand. The number that's in the denominator is the root. So think about it like being below ground. If it's below the fraction bar, then it's the root, and that would be the index of the radical. I don't know, that may or may not help. The 1 would just simply be 12 to the 1st power, optional to write. Okay, you don't have to have the 1 there because 12 to the 1st power is 12. And that's just rewriting the forms. We didn't do anything to simplify yet. 27 to the 2/3. Here we have an example where that m value in the numerator is going to alter how we write this statement in radical form. Again, we're going to do the cubed root, and 27 is our radicand. But now we do need to include the squared. So this is one way to write it, or a more efficient way, especially if we're evaluating it using the power chart, it's easier to find the cubed root of 27 and then square that answer. But they would both give you the same end result. We had to throw in at least one negative exponent. You know that's going to happen. 64 to the negative 2/3 power. So the first thing you want to do is evaluate that negative by taking the reciprocal of 64. All that does is make negative 2/3 become positive 2/3. Now from here, this could be 1 over cubed root 64 squared, or it could be 1 over just cubed root 64 and then square that answer. Either of those forms would be the correct conversion from rational exponent to radical form. The last thing that we'll do in the video is just go backwards. If I give you the radical form, can you convert it back to its rational exponent? So no longer having that radical symbol, but having an exponent that's a fraction. The 4th root of 7 technically means the 4th root of 7 to the 1st power. To convert it to rational form, take your radicand and make that the base. Now the power is in the numerator, so that's where the 1 will go. And the index is in the denominator. So remember, that's the root, so that's in the denominator. To write this then as a rational exponent, it's always numerator over denominator. So that would just be the 1/4 power. And that's all you do, converting it from radical to rational, 7 to the 1/4 power. Let's try the next one. Square root of m to the 5th power. So remember, if there's no root symbol written, it defaults to a 2. M is the radicand, so when we convert it to rational form, m is the base. 5 is in the numerator. 2 would then be the denominator. That means m would be raised to the 5/2 power. That's its rational exponent. The last one's kind of tricky, so let's take a look. Cubed root of negative 27 r squared. And what makes this one a little bit of a challenge is the fact that the squared isn't with the 27, it's just with the r. Technically, then, this entire radicand should be in parentheses, making its exponent not 2, but 1. And that would apply to both the 27 and the r squared. To convert this one then to rational form, the base would be negative 27 r squared. And the exponent, the 1 would be the numerator, and the 3 would be the denominator. That means this is negative 27 r squared to the 1/3 power. And that gives it a rational exponent. We'll stop here, and then we'll finish up the rest of the notes in class.